So we've been talking for a bit now about planar graphs. Remember, the definition of a graph being planar is that you can draw it in the plane without the edges crossing. This is an example of K4, the complete graph on 4 vertices. I have not drawn it in a planar way, but that doesn't mean I can't. If I take this edge out and sort of loop it around the outside instead, now I've drawn K4 so that we can see that it is indeed a planar graph. The question we had when we started, and we first came with this definition, was, what about K5? If I add one more vertex, what can I do? So if I'm adding this, if I want to build up K5 from K4, I have to take my new vertex and connect it to each of the 4 others. Well, it's pretty easy to connect it to these 2. And in fact, I can just sort of loop around here and connect it to this one. And now I have a problem because I haven't connected these 2 yet. And the question is, can I do it? Is there any way that I can do it in a planar way? And we're going to see how Euler's theorem helps us answer this, and it's actually no. So how is that? K5 is not planar. This is the statement. Let's see how to use Euler's theorem to prove this statement. So what we need to do is pretend it is. So suppose it is planar. If it's planar, then we have a notion of faces. So remember that you have to have a planar graph to have a concept of faces. But if we suppose it's planar, okay, then it has to have some number of faces. Therein's going to lie our contradiction. So we can think about each of these components in this thing. So we have vertices. How many vertices? 5 vertices. Edges, it's the complete graph. So 5 choose 2, which is 10 edges. Okay. But now what are we going to do? Well, now we have to say how many faces. So the number of faces, by Euler's theorem, the number of faces has to equal 2 minus the number of vertices plus the number of edges. So that's 2 minus 5 plus 10, which is 7. Okay, so we have to have 7 faces. But keep in mind that we have a complete graph. So any face is bounded by 3 edges. Every face is a triangle. Okay, so every face, that's not true in general, but it is true here. Every face is a triangle because we have the complete graph. All right, so how many triangles do we need? We have 7 faces, so we need 7 triangles because we have 7 faces. But keep in mind that given any triangle, right, it's going to have 2 faces that share an edge. So an edge abuts exactly 2 faces. So each triangle used in 2 faces. So each edge of the triangle, that implies that we're going to have 21 edges divided by 2, but of course we're going to take the ceiling of this. 21 edges for the triangles, each is used in 2 faces. This implies that we have 11 edges. But we don't have 11 edges. We have 10 edges. And that is our contradiction. So the complete the complete graph on 5 vertices is not planar because we use Euler's formula, the Euler characteristic, and we get a contradiction. Let's do that again with another graph. Let's look at the complete bipartite graph, K3. So now we have 3 different types of vertices. Every blue vertex is connected to every red vertex, and there are no edges within the colors. So here I've tried to draw all the edges, and I got stuck, the same as before. So let's see how Euler's theorem can be used to prove this proposition that K3 is not planar. It's the same flavor of proof. So here, suppose it is. Suppose it is. So again, we're going to count vertices, 6. Edges, well, the bipartite graph has 3 times 3 edges, so that's 9 edges. So what does Euler's theorem tell us about the number of faces? So assuming it's planar, we know that the number of faces has to be 2 minus v plus e. So that's going to be 2 minus 6 plus 9, which is 5. So there have to be 5 faces. Now we're going to do the same thing. What does the face look like in the complete bipartite graph? Well, the bipartite graph, every face is going to be a quadrilateral. So every face is a quadrilateral of some sort, okay? So we need 5 quadrilaterals. So we need 5 times 4 equals 20 edges. Each edge is shared by 2 faces, right? So each edge abuts 2 faces. So that means that we get 20 divided by 2 equals 10 edges. But how many edges do we actually have? We actually have 9. So therein lies our contradiction. We end up needing too many edges. So it's the same flavor of proof. If we just pretend that it's planar, we haven't drawn it right, but suppose it is planar, we still know what the structure of the faces look like, and that allows us to come up with this contradiction. And now the final thing that I can say that we won't prove in this class is the following theorem, which is the characterization that we didn't get before. So G, assuming it's connected, is planar if and only if it has no K5 or K3 subgraph. So it turns out the 2 examples that we just did are the only 2 examples in this sense. A graph is planar if and only if no subgraph is isomorphic to the complete graph on 5 vertices or the complete bipartite graph 3, 3.